Welcome to AI Paper Slop, the YouTube series for technical folks where we summarize the latest AI and tech papers.
And we're skipping the intro today, just getting straight into the details.
Yes, exactly. So, the paper today is WBench. That is a comprehensive, multi-turn benchmark for interactive video world model evaluation.
Right, published by the researchers at Fudan University and the Meituan Longcat team.
And if you are building or, training or evaluating video generation architectures right now, this is basically the current state of play.
It really is.
So WBench evaluates interactive world models across 5 specific dimensions. We are looking at video quality, setting adherence, interaction adherence, consistency, and physics compliance.
Right, and they tested 20 state-of-the-art models using 22 really fine-grained automatic submetrics.
Yeah, across over 1,000 multi-turn interactions. And the core insights are honestly pretty stark.
Yeah, there is no single model that dominates right now.
Exactly. A model's ability to navigate is mathematically independent of its other skills. Plus, camera control absolutely does not equal subject control.
Which is a huge issue.
Right. And currently, a model's physical correctness basically correlates heavily with its raw rendering quality.
Rather than its actual, spatial intelligence.
Yeah. So it is a massive reality check. I mean, we have seen a flood of models claiming to understand physics over the past year.
Oh, totally. Spatial dynamics, physics, all of it.
But this benchmark basically applies rigorous multi-turn pressure to those claims, and the cracks in the architectures just become immediately visible.
Yeah, we really need to contextualize why this benchmark had to be built in the first place.
Right, because the evaluation ecosystem already has tools. I mean, we have WBench, we have WorldScore, World Arena.
Yeah, but there's a massive blind spot in how we have been testing these architectures.
Exactly. I mean, imagine you are evaluating a brand new self-driving car. Using existing benchmarks is sort of like looking at a high-resolution photo of the car on a test track and saying, wow, the paint job looks beautiful.
And it looks like it is going fast, so you pass.
Right, exactly. But WBench is putting that car through a multi-lap, multi-terrain obstacle course.
Where every single maneuver depends on the success of the previous one.
Exactly.
Because the limitation with benchmarks like WBench is their heavy focus on just single-turn video quality.
Right, and prompt adherence.
Yeah, you feed the models a text prompt, it spits out a 3-second video, and you just evaluate the pixel distribution.
Which isn't enough. Even WorldScore and World Arena, which do introduce interactive elements, they kind of fail to rigorously test continuous multi-turn interaction.
Right, a true world model requires an agent to actually take an action, observe the modified state of the world, and then take a subsequent action based on that new state.
Yeah, so evaluating single-turn outputs just tests a text-to-video generator.
Exactly, not an interactive environment.
So the scale of the WBench obstacle course is really what makes it rigorous here. I mean, the dataset is built on 289 distinct test cases.
And those expand into 1,058 interaction turns.
Right, and they made sure the settings were highly diverse. So they are testing nature scenes, urban environments, fantasy settings.
Across all sorts of styles, too, like realistic oil painting, cartoon styles.
Yeah, and they vary the subjects between humans, animals, vehicles. But the most critical distinction they make in the dataset is separating first-person perspectives, or FPP, from third-person perspectives, TPP.
Right, and that distinction is absolutely vital.
Why is that?
Because the rendering and computational demands shift entirely based on the camera's relationship to the world.
Okay, that makes sense.
Like, navigating a space through FPP requires the model to constantly generate new geometry at the edges of the frame.
Oh, right, while maintaining the structural integrity of the environment receding behind the camera.
Exactly. But TPP requires the model to manage occlusion.
Like the avatar moving behind a tree and reappearing on the other side.
Yes. And keeping the avatar's temporal consistency intact while doing that, they are fundamentally different spatial tasks for the underlying architecture.
Which obviously introduces a massive logistical headache. I mean, if WBench is this multi-terrain track testing FPP and TPP, how do you fairly test 20 different models that do not even accept the same inputs?
That is the big question.
Because some world models are purely text-driven. Like, you literally type, the camera moves forward and turns left.
Right, while others operate on 6 degrees of freedom or 6 to off poses.
Right. taking in a translation matrix like delta z equals +1, delta yaw equals -30 degrees.
And some actually operate on discrete actions using W, A, S, and D keys like a traditional game engine.
So how did the researchers solve that input fragmentation?
Well, they designed something called the action router.
Okay, the action router.
Yeah, it basically serves as a unified testing interface. So the benchmark defines a standardized interaction path.
Like moving forward 10 meters.
Exactly. The action router takes that conceptual command and translates it into the native input format required by each specific model's architecture.
Oh, so it feeds a localized text prompt to the text-driven model.
Right. And a translation matrix to the 62F models.
And a W input to the discrete action models. That is so smart. It standardizes the starting line.
Exactly. And using that standardized input, they push the models through 4 specific interaction types across multiple turns.
Okay, so what are the 4 types?
First is navigation, which is purely moving through the 3D space.
Got it.
Second is subject action. So that covers manipulation or tool use by the entity in the video.
Right.
Third is event editing, which involves changing the environment state, like, say, triggering a snowstorm or swapping out a vehicle.
Okay, and the 4th?
Perspective switching.
And stringing those 4 interaction types together chronologically is basically where the architectures begin to buckle.
Oh, absolutely. They fall apart.
But I have a fundamental pushback question here about how they actually manage that degradation.
Okay, what is it?
Well, if I ask a standard video model to move forward 3 times by turn 3, it has usually hallucinated a completely new room.
Oh, yeah. The walls change color. The furniture morphs into something else.
Exactly. So how can a benchmark accurately measure interaction adherence on turn 3 if the underlying environment is melting?
Right.
I mean, it seems impossible to grade navigation in a liquid world.
Well, that structural breakdown is exactly what the pre-processing phase of WBench is designed to panelize.
Oh, really? How does it do that?
So before the models generate a single frame, the researchers use a vision language model, a VLM, to decompose the world setting description into an incredibly strict semantic map.
Ah, okay.
It basically separates the environment into visible elements, so objects that must be present in the initial frame,
Right.
and off-screen elements, which are objects that are mathematically expected to appear only after a specific camera movement.
Okay, wait. So the VLM builds a definitive checklist of the environment's geometry before the test even starts.
Yes, exactly. And it also decomposes the subject into specific appearance attributes and action attributes.
Oh, wow.
Yeah, and this semantic checklist is shared across all evaluations.
So when the model generates the video for turn 3, the evaluation suite isn't just looking at the prompt for turn 3.
Right. It references the VLM's pre-computed checklist.
It knows exactly what furniture should still be visible.
And what should have remained off-screen based on the camera's trajectory.
And what the subject's clothing should still look like.
Exactly. So if the environment melts or hallucinations occur, the setting adherence score just plummets immediately.
Which brings us to the actual grading mechanism, right? Because testing over 1,000 interaction turns across 20 models means human evaluation is mathematically impossible to scale.
Yeah, you cannot have engineers sitting there clicking preferences for every single frame translation.
No way. So they built a 22-metric automated evaluation stack. And they didn't just dump this into one massive multimodal model. They deployed highly specialized models for specific spatial and temporal tasks.
Which is the right way to do it.
Yeah, let's break down how these actually work under the hood, starting with perspective consistency. They use SAM2 for this.
Right. So the segment Anything Model 2 is deployed specifically to track the subject's centroid across the video frames.
Okay.
By isolating the subject from the background, SAM2 calculates how stale the entity remains in the frame as the camera or the surrounding environment shifts.
So it basically measures whether the model can hold the subject's structural mass together during a perspective change.
Exactly.
Now, the spatial consistency metric is where the engineering gets really impressive to me.
Oh, yeah. They combine MegaSAM and DreamSim to evaluate round-trip trajectories.
Right. So if the prompt tells the camera to move away from a desk and then reverse back to its starting position, MegaSAM is used to estimate the camera poses across the video.
Yes, to find the exact return frame that should theoretically match the initial viewpoint.
And once MegaSAM identifies that frame, DreamSim evaluates the perceptual similarity between that return frame and the very first frame.
But, the researchers actually had to build a safeguard into that specific metric.
Wait, really? Why?
Well, if you evaluate consistency purely by comparing the first frame to the return frame, a model could cheat the benchmark by generating a completely static video.
Oh, right, because if the camera simply refuses to move, the return frame perfectly matches the first frame.
Exactly, yielding a 100% consistency score while entirely failing the interaction prompt.
It is the classic AI behavior of optimizing for the metric by doing absolutely nothing.
Yeah, we see it all the time.
So how do they force the model to actually attempt the movement?
They implemented what they call a motion gate.
A motion gate? Okay, how does that work?
The evaluation suite samples intermediate frames from the middle of the trajectory
Okay.
and computes their minimum similarity to the first frame.
Oh, I see. So if those intermediate frames haven't changed enough, meaning the camera never actually moved.
Then the motion gate heavily penalizes the final score. It forces the model to actually navigate the space to earn its consistency rating.
That is incredibly clever. They also utilize Transnet V2 to detect unexpected hard cuts, right?
Yeah, just ensuring the model isn't generating a slideshow of different angles.
But the metric that really caught my eye is the 3D coherence evaluation using depth anything 3.
Oh yeah, that one is fascinating.
Because you can think of depth anything 3 like an AI sonar. It looks at a 2D frame, guesses the depth of every pixel, and tries to build a 3D clay model out of it.
Right.
By reprojecting those pixels based on depth across multiple frames, the benchmark checks if the underlying geometry holds up.
Yeah, so if the model shifts the camera on turn 2 and that 3D clay model suddenly caves in on itself, we know the AI is faking its 3D awareness.
Exactly. And finally, for overall visual plausibility, they use a fine-tuned Qwen 3 model, specifically Qwen 3 VL30B-A3B.
It basically operates as a highly specific diagnostic gauntlet for spatial reasoning.
Okay, but we have to address the meta layer skepticism here. We are using Qwen 3, Depth Anything, and SAM2 to grade models like Kling and Genie.
Right.
We are stacking black boxes on top of black boxes. Why should you, as a researcher, trust an AI vision model's automated score over a human expert's qualitative assessment of what makes a video generation successful?
Well, you shouldn't trust it blindly, and the researchers knew that would be a major critique.
Right. So what did they do?
They validated these 22 automated metrics against actual human judgments.
Okay.
They established a blind pairwise comparison platform where human annotators evaluated the exact same multi-turn outputs.
Oh, nice.
And then they mapped the correlation between the human preferences and the automated stack scores.
And I assume the correlation data is what legitimizes the entire benchmark.
Yeah, the Pearson correlation coefficients are incredibly high.
Like how high?
For dimensions like event edit adherence and spatial consistency, the coefficients range from 0.94 up to a perfect 1.00.
Wow, okay, so the automated stack is not hallucinating abstract numbers. Its evaluations of spatial and temporal control align almost perfectly with human perception.
Exactly, it works.
So we have a bulletproof testing gauntlet. The action router normalizes the inputs, and the 22 metric stack handles the evaluation.
Right.
So when they actually ran the 20 state-of-the-art models, and we are talking Kling 3.0, Genie 3, Metuan's Longcat, Seedens.
The big ones, yeah.
What broke first?
Well, the most glaring finding is that these models do not possess generalized spatial intelligence.
Okay.
A model's capabilities are highly siloed. Specifically, the data shows that navigation is largely independent of other capabilities.
Meaning a model might be able to perfectly execute a complex 6-do-af camera translation, like panning left while moving forward.
Yeah.
But doing so causes the global lighting to shatter or the background to dissolve.
Precisely, which leads to another critical disconnect, camera control versus perspective consistency.
Oh, right, because the benchmark proves that a model successfully moving the camera does not equate to maintaining control over the subject.
Not at all. I mean, we frequently see models generate breathtaking drone shots flying through a sprawling, static city.
Yeah, the geometry looks flawless.
But the moment you ask that same model to pan the camera while tracking a human walking across the street, it fails.
Right, the person's legs phase through the pavement or their torso scales disproportionately.
Exactly.
Because the architectures are optimizing for global pixel distribution.
Right, they're trying to make the whole frame look aesthetically pleasing.
Rather than maintaining the discrete, rigid structural integrity of an individual entity while the camera matrix shifts.
Exactly, so we know they struggle to hold a subject together during a single movement.
So what happens when you compound that movement over 3 or 4 interaction turns?
The degradation is severe, but it is uneven across the interaction types.
What do you mean by uneven?
Well, navigation falls off a cliff almost immediately. Moving from turn 1 to turn 2, the spatial error compounds so aggressively that the model loses track of its coordinates.
Wow.
However, event editing, like keeping it snowing in a scene, that degrades much slower.
Oh, that makes architectural sense.
Right.
Yeah, maintaining a global style transfer like snow across diffusion steps is computationally much easier than calculating and maintaining rigid 3D geometric matrices over multiple camera movements.
Exactly. It is the difference between applying a filter and running a physics engine.
Which brings us to the most concerning correlation in the entire paper.
Yeah, this is the big one.
The researchers found that physical correctness strongly correlates with raw rendering quality rather than spatial control ability.
Yes. This is the core illusion of the current generation of video models.
The physical compliance we perceive is largely a byproduct of high-fidelity texture generation.
Exactly.
But I have to play devil's advocate here.
Okay, go for it.
If a model renders a completely photorealistic splash every time a rock hits the water, why does it matter if it is texture recall versus a genuine physics engine?
Right.
I mean, from a user perspective, the output is exactly what I asked for. It looks physically correct. Who cares how the neural network arrived at those pixels?
It matters the second you try to interact with that environment beyond a single turn.
Okay, explain that.
Well, the models that score high on physics metrics are the ones with the highest raw video quality because they're relying on memorized patches of high-fidelity training data.
So the model has seen millions of high-resolution videos of rocks hitting water.
Exactly. So it generates a beautiful, physically plausible splash.
Right.
But if you use the action router to change the interaction on turn 2, like if you alter the angle of the rock mid-flight or introduce a second object into the splash,
Oh, I see.
the illusion shatters. The model doesn't actually understand the causal rules of fluid dynamics, mass, or gravity.
It simply knows what a splash looks like in 4K resolution.
Exactly. It is aesthetic mimicking. The model is performing a parlor trick.
Wow. So a true world model needs to decouple its underlying physics engine from its rendering engine.
Absolutely. It needs to inherently know that a solid object cannot pass through a brick wall, regardless of whether that wall is rendered in photorealistic 8K or as a low-resolution cartoon.
Right. The physics have to exist independently of the pixel quality.
And WBench proves we're just not there yet. The models that offer the most reliable, fine-grained spatial control in the benchmark often suffer from lower video quality.
And therefore, lower perceived physical correctness.
Right. The industry has not yet found an architecture that unifies high-fidelity rendering with reliable, multi-turn controllability and deep causal understanding.
That is exactly why this paper fundamentally shifts how we need to evaluate these systems moving forward.
It really does.
Because being impressed by a stunning 3-second video generated from a single text prompt is a solved problem at this point.
Yeah, we are past that.
The new frontier is building multi-turn, interactive, physically consistent environments that do not collapse when you try to walk around inside them.
Having a unified benchmark with 22 validated automated metrics and a standardized action router finally gives the research community a diagnostic roadmap.
Yeah, we now have a clear metric for where the spatial reasoning is actually breaking down.
Exactly.
Well, as we wrap up this deep dive into the source material, I want to leave you with a different angle to consider.
Okay.
As you build or train your next video generation architecture, consider the action router approach.
Yeah, think about the inputs.
If your model can only understand text prompts, but it completely fails when mapped to a 6DOF matrix, do you really have an interactive world model? Or do you just have a sophisticated text-to-video prompter?
That is the real question, because if it can only parse text, it isn't truly understanding the spatial geometry of the world.
Exactly. It is something to keep in mind as these architectures continue to scale. Well, thanks for tuning in to this breakdown on AI paper slop. Keep questioning the pixels, and we will catch you on the next one.